Who's up
Yeah,
next?
so it's our dear Maira up next.
Maira. Okay.
Click.
Someone who needs no introduction.
She's the person who makes sure everything actually works. 16 years of making complex technology perform under pressure. High availability, demanding SLAs, global deployments that cannot fail. But here's what makes Maira Khwaja different. She doesn't just run the systems, she shapes the strategy. AI product innovation at Kwaai. Open source personal AI. Technology that resists being owned by the few. Today, she's bringing that practitioner brain to something the AI world desperately needs to talk about. How to actually evaluate what's under the hood. Ladies and gentlemen, Maira Khwaja.
I'm Maira Khwaja, board officer, community manager, and intern coordinator at Kwaai AI Lab. Welcome to Drag Race, where vector databases are the queens. As mentioned earlier by Riza, Kwaai is an AI lab focusing on research, development, and policy. Our intern work group consists of a very competitive cohort of grad students selected by Riza and myself. And these past few months, the group decided to conduct a study on benchmarking open source vector databases. So vector DBs have quietly become one of the most consequential infrastructure decisions in AI development, leading to a question a lot of teams ask. Which vector database do you actually use in production? So, vector databases are the engine inside RAG, retrieval augmented generation, a term that's been used, I guess, in previous talks as well. And RAG is now the dominant architecture for production LLM applications such as chatbots, enterprise search, coding assistants, and so much more. RAG is how most production LLM applications fetch relevant knowledge before generating a response. But when we went to choose a vector database for our own work, we found that the available benchmarks were deeply inadequate. Most tested fewer than 100,000 vectors, which is a very small knowledge base. Most ran experiments once with no statistical validation. And none of them had characterized the cold start phenomenon, which we'll get into, and that which can distort completely single run results. And we decided to give the community something better. So what did we do? We built 7 production vector databases: Chroma, FICE, Milvus, OpenSearch, pgvector, Quadrant, and Weaviate, across 9 corpus sizes spanning 4 orders of magnitude, and crucially, n equal 10 fully independent runs per config. Fully independent means we completely reinitialized the database, tore it down, rebuilt it for every single run, because this is the only way to capture true run-to-run variability, including cold start effects. We use the Sentence Transformers Mini LM L6 V2 model for embeddings, which is one of the most widely deployed open source embedding models in production RAG systems. Everything ran on a single Apple M2 Max node inside Docker with 16 gigabytes RAM and 4 CPUs. And for outlier detection, we use the modified z-score method with a threshold of 3.5, which is way more robust than standard z-scores for heavily tailed distributions you see in benchmarking data. Okay, so getting to the findings. This chart shows median P50 query latency at 50,000 chunks, a realistic small to medium RAG corpus. So obviously, Chroma is the clear speed winner. 7.7 to 8.4 milliseconds, and that number barely moves as the corpus grows. If you have a sub 10 millisecond SLA requirement, Chroma is the vector DB to go with. The result I find most compelling is PG vector. At 9.9 milliseconds and 101 queries per second, it places second, ahead of every dedicated vector DB we tested. If you're already running PostgreSQL in your stack, you may not need to add new infrastructure. This is one of the most actionable findings in the paper. Bias is worth noting too. It's the only system we validated all the way to 2.2 million chunks with full n equals 10 rigor. It's slower at 50K, but it keeps working reliably at scales that HNSW systems can't reach. On OpenSearch, it shows 35 to 60 millisecond latency, and it failed to complete testing beyond 10K chunks due to timeouts. Now, the root cause of that is architectural. OpenSearch is fundamentally a full-text search engine built on Lucene with vector search added as a plugin. It's an excellent search engine, just not designed for vector-first workloads. Okay, finding number 2. HNSW gets faster as it grows. And this, to me, was counterintuitive. Because if you think about databases the normal way, more data means more work. But looking at this graph, you can see Chroma's line on this chart, at 1,000 vectors, the latency is 30 milliseconds. But at 50,000 vectors, with 50 times the data, the latency dropped. So latency dropped as corpus got bigger. The answer to that is HNSW graph structure. Hierarchical, navigable, small world builds a multi-layer graph over your vector space. The key word being hierarchical. With only 1,000 nodes, you can build 2, maybe 3 layers. And that's not enough structure to route queries efficiently. But with 50,000 nodes, you get 6 or 7 layers, rich, long-range connections. And the graph can route a query to its nearest neighbors in a tiny fraction of the hops. The practical implication here is important. If you're benchmarking an HNSW DB on a small test dataset, you're not getting representative performance numbers. And you might conclude that Chroma is slow when actually it's just immature. This also explains why Quadrant's line dips and then recovers. It hits a local rough patch around 10K nodes as the graph is transitioning between layer configurations. To our knowledge, this warm-up effect on HNSW graph maturation has not been systematically documented in the literature at this scale. So that was a very interesting finding. And finding number 3, cold start phenomenon. If you look at the red bars, raw ingestion consistency coefficients of variation. Quadrant is at 123%, Weaviate at 107, OpenSearch at 93. And if you saw those numbers from a single run benchmark, you'd probably cross those DBs off your list. But now look at the green bars. It's the same data set after modified z-score outlier removal that we spoke about earlier. When a database starts from scratch, building HNSW graph structures, warming JIT caches, setting up write-ahead logs, it takes dramatically longer than it does in its steady state. That cost is real, but it's a one-time cost. It has nothing to do with how the DB performs once it's running steady. PG Vector and FIS didn't need this correction because their initialization paths are simpler and more deterministic. After outlier removal, all the systems achieve what we'd classify as exceptional or excellent consistency. The meta lesson: if a benchmark claims a DB is inconsistent, ask how many runs they did. If the answer is 1, they measured boot time and not performance. The last finding, and there's 2 surprises that we had here. Retrieval quality follows a U-shaped curve across corpus sizes. At 175 vectors, average cosine similarity is 0.688. Drop to 1,000 vectors, and it falls to 0.5. Then, as you add more data, it recovers, peaking around 50K, and eventually plateaus past 250K. The dip at 1,000 chunks is again the immature HNSW graph story. Sparse structure means poor routing, means lower quality top K results. So the production guidance from this is to deploy with a minimum of 10,000 chunks. That 1K quality valley is a real trap that would quietly degrade your RAG application's answer quality. The second finding, and this will simplify your DB selection process enormously. All of the HNSW DBs return virtually identical retrieval quality. The variance between them is less than 0.0001. They're all implementing the same underlying algorithm. So, of course, they're going to return the same results. What this means practically is we need to stop comparing vector DBs on retrieval quality in our evaluations. We need to compare them on latency, throughput, consistency, and operational features. So, which database should you use? If your RAG application needs sub 10 millisecond query latency, Chroma is the clear winner. If you're already running PostgreSQL in your stack, then you should consider pgvector. Before you add Quadrant or VB8, check whether pgvector meets your SLA. Number 3, if you need to scale past 100,000 chunks, FIS is the only option we proved worked at 2.2 million vectors. And then if you need enterprise features, authentication, filtering, a rich API, Quadrant is our recommendation. On OpenSearch, it is a co-located sponsor here at SCaLE, and for good reason. It's a fantastic open source engine with a huge community. If you're already using OpenSearch and want to add small-scale auxiliary vector search, that's a reasonable addition. Milvus and VB8 sit in the middle of the pack, solid options if their ecosystem features matter to your team. And lastly, 5 things to remember. Chroma wins on raw speed, but pgvector is second. HNSW graph maturation is a real phenomenon. Performance improves as data grows. High variance in benchmarks almost always reflect cold start initialization. With n equals 10, outlier removal, we can tell the true story. And then all HNSW DBs return identical retrieval quality. So we need to stop evaluating on this dimension. Choose on performance, choose on features, and the operational characteristics needed. And then plan your memory ceiling before you commit to a stack. HNSW tops out at 1 to 2 million chunks. FIS can go to 5 million plus on the same hardware, so know your scale target. And everything is open source, and we want you to reproduce, challenge, and extend this work. Lastly, if you are interested in our intern program, I would love to encourage you to go to Kwaai.ai and join as a volunteer, and then send me an email, and Riza and I will evaluate. Thank you, everyone.